Hello, good afternoon. I'll be doing part 1 of lab 4, which is stepper motor control. We're dealing with the stepper module here. I'll just show it to you. This circular structure, so what we're actually aiming to do is we are trying to make this lighted LED move around in a circle, either in the clockwise direction or the anti-clockwise direction. We can see the particular outputs of this laboratory, and you can see there are 3 states: S0, S1, S2 and S3, I can show you the state machine of this particular structure. And if you start off at the first state, which is 1 0 0, and then you have the second state, which is 0 0 1 0, and the third state, which is 0 1 0 0, and the final state, which is 0 0 1. So what happens is when we get an enable step input, which is represented by the first input here, the circuit moves from one stage to the next stage. And if there's a second input, which is for the clockwise or the anti-clockwise, which is indicated by the second input, the state moves in either the clockwise direction or the anti-clockwise direction. So describing this particular scenarios is this truth table, and as you can see, these are the states, and these are the JK flip-flop inputs. So the truth table related to this is this one. So as you can see, the prime impedance have been identified here, and the final characteristic equation of each input has been described. After that, you get the output functions, which describe the states, as you can see. And for that, you have another set of Karnaugh maps to get the output functions. And as you can see, for this one, for the first 0 0 state, you get A complement and B complement, as you can see, and this is that. And then you get the second state, A complement B, which is this. And for 0 2 state, AB complement this, and for the final state, AB, which is this. So then we have the schematic diagram representing these particular truth tables and characteristic functions. As you can see, there are 2 flip-flops, and then there's an XOR gate, and then the final outputs, which are AND gates. So that can be seen here on this particular breadboard. And here we have the EN input, and this one is the CW, which is the clockwise or anti-clockwise input. So I'll just do a demonstration of this. And as you can see, if I hold onto this, you can see that the stepper module starts to move. So if I let go of it and switch this off, then you can see it stops. So if I want this to move in the other direction, I can just press the clockwise, and then you can see that the output changes. And that brings an end to the presentation.
Hi, this is Hova. So today I'm going to talk about part 2, linear feedback shift register. So in this lab, right, first we're given this diagram 3-bit maximum length LFSR. So from this diagram we come up with our own diagrams, so schematic for LSFR. So we're using the 74 C164 for this to come up with this circuit. So in the first place, right, the things that we construct, right, it will look by itself in 0 0 0. So according to this question, right, a 3-bit LFSR using the equation S3 and blah blah blah. Okay, so how? So by connecting to the switch to by connecting number 8 is here, connect it to the switch, right? Our HC164 to the switch, and by pressing the switch, right, the loop will break. So now, as you can see, now it's go from 0 0 1, go to 1 0 1 1 1 0, then and so on. So this is how we break the loop. So what happened? So how can the second SOR help? So the second SOR act as a set button. So it provide a 1 into the circuit, and then now the circuit now become 1 0. So everything will become 1, and then it will start counting. Okay, so now I will demonstrate on this diagram on the oscilloscope. So first thing first, you need to change the clock module to 5K frequencies, so you can see it clearly. So this is the clock, and this is our SR. So if you zoom, so the SR, right, it seems to be random, but it's actually fluctuate, but it's the same pattern. But if you zoom in, right, you will see the line go out and down, out and down. So this is how we call it random. So the frequency, right, from here, we get 0 1 0. So 0 1, yeah, 0 0 0 1 0. Okay, 0 1 0 0 1 0, and then 1 0 1.
0, then 1 1 1, and then again goes
And
back
then-
to this, as in the diagram over here.
Yeah.
So from 0 0 you get 1, then 0, then 1 1 1, as in the same diagram
Sure.
we got here.
Yeah,
So
0 1
according to this,
0
it's
1
not
1 1.
random over here. It's not random.
Yeah, it's not random. It
So-
look like random, yeah. So this is all for the 3 bits maximum length LFSR. Thank you. So I will continue to talk about 7-bit LFSR. So in this circuit, right, 7-bit LFSR is almost similar to 3 bits. The difference is the sequence of the length, which is 1 2 7. As you can see, right. So if you change the sequence, right, it will become larger. Just that the space is not enough to display all the 1 2 7. So what we do here is we change the position of S0. So now we connect the S0 to Q7, and of the head C164, and the S1 to the Q4, and then S1 become our S3. So here, this is our output. So how to unpause this one? Right? Okay. So if you zoom in zoom out, zoom in. So let me explain. Okay. Okay. So if you zoom out, right, you will see that this X3 is fluctuate. So here, right, observe the new output on SO with the SO that the PRSBS appear random. Yes, but since this is a pseudo random, right, it appear to be random, but actually it's only like fluctuate around out and down. So it look like random, but actually it's not random. Okay, this is all from me. Thanks.
Okay, now we are going to do the part 3, where we wanted to design a milli state diagram with the sequence of 0 1 1, and this is our milli state diagram that we got here, and this is our table. So as these are the present, like ideal 0 0, these are the input, and this is the output we get. So all these are in the table, and with the truth table we have got the values of DA, which is BW, DB, which is W dash, and F, which is AAW. So after putting all this into our board over here, into our board, and also these are our schematic we have got here. These are our schematic, and as you can see, the output, which is this, is connected. This is the input, which is connected to the channel 1, and this is the output, which is connected to the channel 2. So as you can see, this is our run switch where it's on now, and we have set a frequency to 500 kilohertz, and in this case we have used 4 ICs, which is HC74 IC, HC86 IC, HC00 IC, and HC08 IC. So as you can see, this is our graph we got over in the oscilloscope. So as you can see, this is our normal what we got here. So to get a clear view, we have stop this, and if you zoom it, you can see like again for a clear view I will restart it. So I'll stop at this point. So if you zoom it, as you can clearly see, when there is a 0 1 1, you get a positive, you get a input output of 1, and also here like 0 1 0, you get a input output of 1. So I can at this point, you can see it now, like when there's 0 1 0 0 1 0, you get a output of 1, and also in this case where there's a 0 1 0, you get an output of 1. So this is our third part, and this is what have we come up with, and that's it.